Derivatives measure the rates of change. So let's look at the rates of change. So anything that changes with respect to some other quantity, that's when we can use a derivative. And what do we know? If we're thinking about the curve, the steeper the curve, the faster the quantity we're measuring is changing. So here's my curve. If I'm at this position on the curve where I've labelled P, now at this stage we're going up, if you like. Well, what we do know is the slope of the tangent at that point would be positive. So that's simply what we say. Well, it's increasing, it's going up. So if it's got a positive derivative, we know our function's increasing. Then of course we get to the top, the peak, and at that point the tangent is horizontal. It would have a slope of 0, and we give it the very creative name of stationary. It's not going up, it's not going down, it's stationary. And then of course we get over the other side, and now our tangent has a negative slope, and we call that decreasing. Basic idea. If I have 2 points on my curve here, and I draw in the sequent, the slope of that sequent measures the average rate of change. Okay, so when we get 2 points. As opposed to just 1 point, I draw in the tangent. The slope of that, our derivative, gives us the instantaneous rate of change. And the reality is, that's probably what we're more interested in. A simple example, when you're in a car, you don't want to know your average speed, you want to know what you're doing at that point in time. I mean, if you get pulled over by the police for speeding, you can't go, oh no, but if you take my average over the last hour, actually, I'm below the speed limit, I'm fine. It's got to be the instantaneous they're interested in. Let's look at this one. We've got a water tank, it's being emptied. We know at any point in time there's Q litres of water in our tank, and they've given us a measurement for that volume. There it is, 1,020 minus T all squared. So what's the rate of change? What's the rate this tank is being emptied? There's Q, so basically they're saying to Q to T. How does the quantity change with respect to time? We do our calculus, and there it is. Now the rate tells us the units. Quantity here, Q, with respect to time, and Q they've told me is in litres, time they've told me is minutes, so the units must be litres per minute. How long does it take to empty the tank? We now have a couple of equations we can work with. We've got one for the quantity itself and another for the rate. Well, it's the quantity I want to know for this one. So when is it empty? Well, it's be when the quantity is equal to 0. There's none left in there. And we just solve that simple little quadratic and we get T equals 20. So we know, all right, after 20 minutes it'll be empty. At what time is it flowing out at a rate of 20,000 litres per minute? This is where we've got to be careful, because our rate is actually negative 20,000 because it's decreasing. We say when it's decreasing, the derivative would be negative. Solving that, we get, oh, it's after 10 minutes. What is the average rate? So the slope of that secant. First 5 minutes must go from T equals 0 to T equals 5. I'm going to need to know the quantity at those times. So in T equals 0, got 400,000. T equals 5, I've got 225,000. So now I find the average rate. Difference in the quantity over difference in the time. I get negative 35,000. Okay, there's my average rate. 35,000 litres per minute. What we're really interested in, though, are the equations of motion. This goes back now, I was talking about the other day, the two mathematicians who discovered calculus. Gottfried Leibniz, a German. I always think it's interesting to see how old they actually were when they came up with these ideas. He was only 28 when he came up with his idea of calculus, and it's actually his notations that we tend to use. Newton, of course, is the other one. He was even younger when he did it. He was 22. Put that in perspective, think about that, 22, and came up with one of the greatest thoughts in mathematics has been for quite some time. This idea of calculus, being able to measure rates of change. It's his dot notation we use when describing the motion. Displacement, velocity, acceleration, these are the three key things. Displacement, we often use x because we tend to think of things moving along the x-axis. And it doesn't have to be x, it could be any pronumeral you like, I guess. And what is displacement? It's distance from a point but with direction. So the plus and negative has some meaning. It tells you which way, which side of the origin you are. Velocity is the rate of change of displacement. So our notations will obviously be for velocity. You've got the dot notation there, which is Newton's notation, x with a dot. Then of course you could write it as dx to t, rate of change of displacement with respect to time. So it's speed, but again, with direction. The plus or minus means something. Acceleration, that's the rate of change of velocity with respect to time. That means now we have several different notations we could use. A, obviously, for acceleration, but it's the first derivative of velocity, so I could have v with a dot. Or it's the second derivative, differentiated again, and we have x with two dots. Or it's dv dt. Or the way we write the second derivative, d2x dt2. We're not squaring the derivative there, that's just how we write the second derivative. So I'm going to draw up three graphs. I've got well, for want of a better word, a travel graph. That essentially is what a displacement time graph is. It's a travel graph. And from that graph, I'm going to create a velocity time graph and an acceleration time graph. Now, what do we know? We know when the displacement graph is stationary, so up there, horizontal slope, then the velocity is zero. So I could transfer that down onto the velocity graph. Okay, I know velocity is zero at that point. And in fact, we've got another stationary point there. We can transfer that one down as well. We know when the displacement graph is increasing, so for that section there, velocity is positive. So I know on my velocity graph, I must be above the axis. I could do the same sort of idea for decreasing. So when it's decreasing in that section there, the velocity graph must be negative. So I know I'm down there. When is the velocity graph stationary? It's going to be there. What am I looking for? It's actually when my displacement graph inflects. Inflects is basically when the curve twists, if you like, changes its concavity. So that's round about here. Now I don't know exactly the value of it, but I do know it's negative. I'll just place it down here somewhere. Then we get something like that. Now have a look at the curves themselves. That displacement time graph, whilst I don't have an equation for it, it's certainly got the shape of a cubic if it was a polynomial. Think about that. Differentiate a cubic, you're going to get a quadratic. So it's no surprise my velocity time graph looks like a parabola. You could do all the same sorts of things now for velocity and acceleration. Okay, I've got a stationary point here. Transfer it down, that must be the t-intercepts on my acceleration graph. My velocity graph is decreasing, so it's negative. My velocity graph is increasing, so it's positive, and I logically get a straight line, because if that's a quadratic, differentiated quadratic, you would get a linear function. So I have a straight line. That's the basic idea of drawing, well, I'm using them for displacement, velocity and time graphs, but for drawing derivative graphs, you can look at one thing, look for the features and transfer that down to the other one. That's why I sort of like putting them above each other, so you can plot these things directly underneath, transfer it to the graphs themselves. So 9J.